This is an unfinished video I've had sat on my hard drive for a couple of months, and I thought I might as well just throw it on YouTube for posterity and free up some storage. The video is a code walkthrough of a neural net I made in Ruby. It's a general purpose neural net, but we've trained it to recognize handwritten digits. I mean, in theory, you could train it for anything you like, but it's not very efficient. It doesn't use any matrix multiplication. It's purely a learning resource. The code's all up on GitHub if you want to have a play around with it. I wouldn't use it for anything performance critical, but if you have watched the Free Blue One Brown neural net video series and would like to see how one of these would look in Ruby, feel free to go and pull down the code. The video is a bit rambly and jumps around as I didn't write a script, I just said what came into my head, and it cuts off at the end because I've not finished the video and I've got a bunch of other projects I'd rather work on, so here it is. This file handles training on neural net, and in this case we're training the neural net to recognize handwritten digits using the MNIST dataset, which is a bunch of images of handwritten digits that have been labeled. So let's take a look at the data we're working with. If we just take a look at one of the examples, let's see what that example is. In this case, it's a handwritten 5, which the neural net sees as an array of pixel brightnesses where big numbers are bright and small numbers are dark. And also we have the label, so we can check if the neural net has predicted the right number or not. So here's where we set up the neural net. We set up an input layer with 784 neurons as the images are 28 by 28 pixels, so there's 784 of them in total. We set up two hidden layers with 16 neurons in each, kind of arbitrarily chosen. And then finally, we set up the last layer with 10 output neurons. We're using this constant numbers here. This is just to let us tweak how many numbers we train the neural net on. We can just train the neural net on two numbers if we want to train it quickly to experiment on things. But in this case, we're going to train it on the full set of digits. Now we set up the neural net, we have a pretty standard training loop. We loop through all the training data epochs number of times. It sees each of the examples 25 times, and we split our training into batch size batches. That's 128 per batch. And then after each batch, we update the weights and biases of our network. For each example in the batch, we take the input and pass that to the train method on the neural net along with the target. The target is a one hot vector where the hot element corresponds to the example's label. So in this case, the example is a 2, and the third element in this vector is active. If the example was a 3, this would be a 0, and the fourth element would be active. If the example was a 0, the first element of the array would be active. Let's take a look at this train method. So first of all, we make a forwards pass through the network with our input, which is the array of pixel brightnesses, and then we make a backwards pass through the network with our target vector, which is the output we want the neural network to give us, and it's in the backwards pass through the network where we update the weights and biases depending on how far off what the network output is from what we want. So let's take a look at this feed forward method. This gets called with the array of pixel brightnesses. That's passed to the first layer, and then the output from the first layer is passed to the next layer. This is done for all the layers in the network. Let's drop some breakpoints in here and take a look at these activations. Initially, the activation vector is the array of pixel brightnesses passed to the network, and this gets passed to the first hidden layer. Then after an iteration of the loop, the activation vector is the output of the first hidden layer, which has 16 neurons in it. And each of these elements represent how active one of these 16 neurons was given the input array of pixel brightnesses. Then we do another iteration of the loop, and the output of that first hidden layer is passed to the second hidden layer, and activation vector is now the output of the second hidden layer, which again has 16 neurons. Finally, we do our last loop, and activation vector is now the output of the output layer, which is 10 neurons. And the most active of these neurons represents the neural net's prediction, which looks like it's this 0.8 here. So the neural net has predicted a 9. Let's go and quickly just take a look at this prediction method. It's pretty straightforward. The neural net's prediction is just the index of the most active neuron. If we take a look at the neurons, they store their activation for later, which is just how I've implemented this neural net. Now we've done our forwards pass through the network, we've generated and stored the activations of each neuron. Let's take a look at the backpropagate method. Backpropagate is called with the target vector, and it's in this method where we work out how to adjust the weights and biases of the network to reduce its cost. The cost of the network is the difference between the target vector and the output of the network. So I can type. In this case, the target is a 7, and it looks like the network has predicted an 8. That looks like the most active neuron. We work out the cost of the network by comparing each element in the target vector with the activation of the corresponding neuron in the output layer. So in this case, the first element in the target is a 0. This is pretty close to 0, so we won't need to adjust it too much. If we take a look at the 9th element, here we're close to a 1, but in the target vector that's a 0, so we're quite far off, and we'll need to adjust the weights and biases of the network to bring this value down. In this case, the example we're trying to predict is a 7, and the network has predicted a 8. So here in the code is where we loop through each neuron in the output layer. We compare it against the corresponding element in the target vector, and then we do some partial differentiation to work out how a change in the bias of this neuron affects the cost, and how a change in each of the weights of this neuron affects the cost. Now, we actually collect these and we store them on the weight and bias objects respectively, as what we've calculated in here is how we need to adjust the weights and biases for a single example. And we want our neural net to generalize, so we store the adjustments for each example, and then after a batch, we update the weights and biases by the average change we want to make, given all examples in a batch. I'm not going to go into how we calculate how much we need to adjust each weight and bias. That's a bunch of partial differentiation. You can look at the comments in the code. I'd also recommend Free Blue One Brown's excellent series on what backpropagation actually is doing. All this we've just looked at is just covering how we update the weights and biases in only the output layer. The hidden layer is a little more complicated, as each weight and bias in the hidden layer affects the cost of the network via many paths to the output layer, as each of the layers are fully connected. That makes working out how we need to adjust each weight and bias in the hidden layer a little more complicated. Again, this is nicely covered in Free Blue One Brown's videos. Again, it's just more partial differentiation. Now we've worked out how we need to adjust the weights and biases for the hidden layers, and for the output layer, we repeat that process for each example in the batch. And after each batch, we update the weights and biases with the average adjustment. Then we loop through each of the batches in this epoch, and then we repeat the process 25 times. This process takes a while, as this isn't a very efficient neural net, as it doesn't use any matrix multiplication, so we can't offload the work to the GPU. This is just purely for my educational purposes. When training's complete, we then save the neural network to disk, and we are good to test the neural network. Now I'm going to kick off a training run. This will take a little while to complete. We'll stop the video here and check back in when it's finished. As I mentioned at the start of this video, it just ends abruptly. This is where it does so.